Hello, welcome to Maths with EJD. In this video, I'll be talking about discrete Fourier series and transform. Okay. Previously we have talked about complex Fourier series. We've talked about Fourier transform. Of course, we saw how complex Fourier series helps to uh, make Fourier series more compact because then you only are concerned about one coefficient one Fourier coefficient, and then for the other one, Fourier transform, you see how it generalizes Fourier series to non-periodic functions because normal Fourier series is concerned with just periodic functions. So here, let's look at discrete Fourier series and transform and see how that works. So first off, can we talk about the key concept? Key concept. So here, the discrete, the discrete Fourier transform, DFT for short, applies Fourier analysis. It applies Fourier analysis to a finite set of data points. So you have a finite set of data points. All right. So imagine that for n samples, x naught, x1, all the way down to xn minus 1, okay, the discrete Fourier transform is defined as xk. It's defined as xk equals summation from n equals 0 to n minus 1 of xn e raised power minus I 2 pi over n, then kn. So you have kn. So, and of course, our k is 0, 1, all the way down to n minus 1 also. Okay, that's the idea. So this is what you have for discrete Fourier transform. So that's like straight to the point, right? Now, let's take an example to actually get a grasp of what this whole thing is about. So example, so compute discrete Fourier transform of xn equals 1, 2, 3, 4. So 1, 2, 3, 4. So here now you see that tells us that big N is equal to 4. That's all this is about. Big N is equal to 4. So let's go step by step now. Step one, we apply the discrete Fourier transform formula. That's the first thing we do here. Okay. So we say for each k, which is, of course, you start from x naught to n minus 1. So an n is 4 here. So we say k equals 0, 1, 2, 3. 3 is 4 minus 1. Okay. So 0, 1, 2, 3. That's where we go. And then that tells us that our xk is going to be summation from n equals 0 to 3 of xn e raised power minus I 2 pi over 4. I think that was what we had there. Yeah, big N, 2 pi over 4, then Kn. And we already know that K is from 0. This is K small n, sorry. And we already know that K is equal to 0, 1, 2, 3. So that's step 1. For step 2 now, step 2, we want to calculate. Step 2, calculate each xk. Calculate each xk. So we start. So say for K, yeah, I mean, calculate each xk. So we just go. So for x naught, that's when k is equal to 0 now. Or maybe I should just do that. Let me just say for k equals 0, it means we have x naught equals, hmm, so because k is 0 here, let's see what happens there. So for k is 0, now you can see k is 0 here, 0 times everything. So that's e raised power 0. And as a result of that, we just simply have, for k is 0, I think, let me explain that. For k is 0, so we have n equals 0 to 3 xn e raised power minus 0 because there's this k up here. So we just have summation from n equals 0 to 3 of only the x ends, right? In that case, the x ends are just the, like from the definition, right? The x ends are all these x naught, x1, x. So the x ends are simply uh what we have for k. So because k is 0, 1, 2, 3, so that means this is x naught, this is x1, this is x2, and this is x3. That's basically the idea here. So it seems it means then that big X naught is equal to okay, this is from 0 to 3, right? So we have okay, let me see the formula again. Yeah, it's up to n minus 1. Yeah. So we just have trying to understand this. Okay, this is 0. X naught. That's summation from 0 to 0. Yeah. I want to be sure this is clear. So, of course, this is 1 right here. So, and this is up to n minus 1. Yeah, I think this should be, so x naught now will just have to be from the formula 0, 1, 2, 3. So when x is 1 now, when k is 1, normally this is 1 of the half pi n, then k is 0. Okay, k is 0 of the e raised minus 0, that's 1. X naught is 0. Okay, so let me be sure. So we have 0, 1, 2, 3. So I want to be sure why. How did I even get here? Oh yeah, sorry. Sorry. I think that is 0 to 3, right? So for each, when k is 0, this is xn. Oh, these are the values of our xn. Yeah, I think my explanation here is wrong. Okay, because we already have our xn. Sorry, I should have seen that in the original question. These are our xn's. Okay, yeah, that's bugged me a little bit. So yeah, our xn's are 1, 2, 3, 4. I was really wondering. Okay, 1, 2, 3, 4. Nice. So we're good to go now. So we can say that our x naught is simply just all the summations from this is x naught, x1, x2, and this is x3. That's all we need. So we have this now, x0 plus x1 plus x2 plus x3. So that means that x0 is simply equal to 1 plus 2 plus 3 plus 4. And the smart way to add from 1 to any number is take the last number, multiply by the next number after it, and divide by 2. That's 4 times 5, 20 divided by 2, 10. Although this is easy to do, 1 plus 2, 3, 3 plus 3, 6, plus 4, 10. And we are good to go. So x naught is 10 in short. That's taken care of. So we go for the next one. Say for k equals 1, for k equals 1 now. So you look at the expression again. So it means we have x1. So that's x1. And what does that say? So that's x1 equals summation from so now our n is 1. So we're moving from it's k that is 1. So k is 1. So we move from summation from n equals 0 to 3 again. So we have xn, then e raised to power, e raised to power, so e raised to power minus I 2 pi over 4. Okay. Now k is 1. So that's 1 times n. So we just have that to be n, okay? Because k is gone. So let's do this now. We can now open this up. So x1 is equal to when n is equal to 0, so we have x naught e raised to power. I mean, we just have x naught, right? Because this will be x naught e raised to power 0. Because n here is 0 now. So plus x1 e raised to power minus I. Well, 2 pi over 4 is just pi over 2. Now n is equal to 1, right? Now n is equal to 1. Yeah. So that's just minus I pi over 2. Then the next one we have x2, all right? x2 e raised to power. Now n is 2, right? So this will just give us e minus I. Then 2 pi over 4 is half pi. Half pi times 2 is just 2 pi, right? That'll be what did I do there? Half pi times 2. That would just be pi, yeah. That would be pi plus x3. So x3 now, n is 3. So we have e raised to power minus I 2, 2 pi, I mean 3 pi over 2. That'll be 3 pi over 2. So that means our x1 is equal to x naught. Of course, x naught is just 1 plus the next thing is 2 e raised power I pi over 2. Then the next one is x2 now is 3. Don't forget all this x naught, x1, x2, x3, please. Don't forget. Then x2 now is 3 e raised power minus I pi. Then next one is 4 e raised power minus I 3 pi over 2. That goes. So in that case, if we evaluate all of these things, we know that xi can be said to be 1 plus 2 into e raised power minus I pi over 2. If you do it in angular form, like if you say cos, that's more like cos 90. I won't bother about it, but I'll just say it and I'll do it. So I raised by minus that'll be cos. Pi over 2 is 90. So cos 90, which is 0, right? Minus sine 90, which is 1. So that's why this will be 0 minus 1. So this is minus 1 here, plus 3 into here again we have cos 180. I think cos 180, I think that should be cos 180 should be 0, I think. I'm not sure. Then sine 180, I think, is 0. But whatever that is, that's simply cos 180 minus sine 180, basically. And that ends up giving us 1. Then we have 4 into same cos 3 pi over 2 minus sine 3 pi over 2. So that ends up giving us minus 1. So at the end of the day, x1 is just everything x1 is actually 0 minus 2i. That's simply 2i. X is equal to minus 2i. If you tidy up all of this, don't forget, using the Euler formula, you know that e raised power minus I pi over 2, for instance, is cos pi over 2 minus sine pi over 2. That's what I'm doing. So you do it for this, you do it for this one, also do it for this one. That's what will lead to. So this one is this one. So this expression is what gives this. This expression gives you this, and this expression gives you this. So if you punch your calculator for that, you can get that. So at the end of the day, x1 is minus 2i. So that's, and we want to do for all the four, right? From 0, 1, 2, 3. So we have done 1. So let's go for, so we say for k is equal to 2 now. For k equals 2, all right, for k equals 2, we now have x2, which is summation, x2, which is summation from n equals 0 to 3, n equals 0 to 3 of x, I think that should be x, okay, that's still xn, e raised power, now k is 3, the original expression, k, so that's pi over 2 times 3n. So that's pi over 2 times 3n. That's 3 pi over 2. That's 3 pi over 2n. Okay. That's 3 pi minus I, 3 pi over 2n. Something like this. So we can now start the expansion. So this x2 now is equal to, when n is 0, you have x naught. So, and n is 0 up here. So x naught, that's all you have, because this one will go to 1. So the next one is x1, then e raised power, this is 1. So e raised power minus I, 3 pi over 2. Okay, for x2 now. Oh, what's that now? X2. N is, now we're saying n is 1. Okay. Let me see. K is 2, right? In the original expression, K is 2. So K is 2. So this is half. So 2 cancels 2. Okay, so 2 cancels 2. No. Yeah, K is 2. So if K is 2, so we just have pi. This can be confusing, really. Okay. Yeah, because K is 2, right? We just have pi here. So we just have pi n. So because of pi n now, I think this should just be, this is pi n, pi n. So when n is 1, we just have I pi, basically, for x1. So yeah, minus I pi, then plus x2, because n is 2 now, plus x2 e raised power minus I 2 pi. Then for x3 now, so we have x3 e raised power minus I 3 pi. Okay, e raised power minus I 3 pi. Okay, so I won't do this explicitly too much any longer. So at the end of the day, if you tidy up all the, that's 1 plus 2 e raised power minus I pi plus 3 e raised power minus I 2 pi plus 4 e raised power minus I 3 pi. So if you tidy all of this up, you see that x2 will just give you minus 2. Or maybe I can just still try. So I have 1 plus 2 into minus 1 plus 3 into 1 plus 4 into minus 1. So you have x2. x2 is equal to minus 2. So that's for k equals 2. So for the last one, I won't go all that long. So I just say for k now equals 3. So for k equals 3 now, I just go straight. It means our x3, I'll give the last line and the final result. Our x3 will just be 1 plus 2 e raised power minus 3 pi over 2 plus 3e raised power minus I 3 pi, okay, plus 4e raised power minus I 9 pi over 2, So from there, we just have x3 equals 1 plus 2 into I plus 3 into minus 1 plus 4 into minus I. Okay, so that means that x3 is just going to be 2I. So now we have got all the results. Okay, we have x3 equals 2I. We have x2 equals minus 2. We have x1 equals minus 2I. And then we have x0 to be, x0 is 10. Okay, those are the results we have. So what do we conclude? Okay, so we now say, so the final step, I mean, we are following steps, right? That was step 2. So step 3 is to write the final result. Step 3, write result. Write result. So we just say the frequency components, the frequency components are x, which is equal to 10 for the first one, minus 2I for the next one, minus 2 for the next, and then 2I for the last. So we are bringing all these results together. 2I minus 2, minus 2I, 10. Rather, that's 10 minus 2I, minus 2, 2I. So those are the components corresponding to all the xn's we had initially. So all the xn's, 1, 2, 3, 4. Okay. So all the xn, which are also 1, 2, 3, 4. So each of those correspond with each of this. And that is how that goes for discrete Fourier transform. I'm very sure down the line, I'm going to do maybe use some maybe Python to show how this looks like. Okay, I'm going to use Python to do that, and I believe it's going to make a whole lot of sense. And you definitely don't want to miss out on that. So be sure to sign up. Be sure to sign up and to this channel. Hit the notification bell also, so you can always get alerted each time a new video is released. Comment, let me know how helpful these videos are for you. And of course, then like and share so that more people can have access to this great channel. But until I come your way again, do have a great time. Bye.